So what are we doing today? Today we're going to be able to identify and use the incenter and the circumcenter of a triangle. We'll talk about what that is. Uh, the point of using a big math word here, the point of concurrency of the angle bisectors of a triangle and the point of concurrency of the perpendicular bisectors. We'll talk about how we get those, what we do with them, all that good stuff. So let's begin. So with the perpendicular bisectors, if we take the perpendicular bisector of each one of these sides, we find the middle of each side and we draw a perpendicular line through that side. Turns out that they all land in the same exact spot. That is to say they are concurrent. That's the special vocab word that means that all three of them touch at the same spot. So what makes this spot special is that it's the exact same distance away from these 3 points, the 3 vertices of the triangle, A, B, and C. And so basically, if you look at what this says here, if you've got the place where the 3 perpendicular bisectors line up, if you measure from that spot to the corners of the triangle, they're all the same. What does this have to do with anything? Well, what this means is actually, and this is the reason why see this vocab word right here, circumcenter. This spot is the center of a circle that's drawn so that the 3 corners of the triangle are on the circle. Basically, the idea is that this spot right here, from where this perpendicular bisector goes, this perpendicular bisector goes, and this one, from here to each corner is actually the radius of a circle. We'll be coming back to this much later. Well towards the end of second semester. But basically, and here's another word, circumscribed. Basically, here's your triangle, and then you draw a circle around it so that all the corners are touching the circle. You say that you have circumscribed a circle around that triangle. So, one of the big things about the circumcenter is that the placement of the circumcenter can help us figure out what type of triangle we're working with. Is the triangle acute? Is the triangle obtuse? Is it a right triangle? How do we know? We can use these perpendicular bisectors. We can use the circumcenter to help us figure that out. So if the circumcenter lies on the inside of the triangle, like it does in this one, then this triangle is acute. All 3 angles are less than 90 degrees. If we have a right triangle, the circumcenter is going to be right there on the midpoint of the hypotenuse. So if you look at the right angle on the triangle, and then you follow it to the other side, find that hypotenuse. The middle of the hypotenuse is where the circumcenter has to be. And then if it's an obtuse triangle, you'll find that the circumcenter lies on the outside of the triangle, on the hypotenuse side. Like you see, it's over here. You would never find the circumcenter on this side. It's never going to be over here on the vertex side. It'll always be on the hypotenuse side over here. Okay, so let's do a couple examples on finding the circumcenter. So here, there's a number of different ways you can do it. I'm going to show you 2 of them right now. The first one is actually drawing it out. So let me get a line here. Remember, we want to find the perpendicular bisector, right? So if we want to find the perpendicular bisector, we have to look. Here's one side. Where's the middle? Well, one corner is at 0, the other corner is at -4, so this middle had better be at 2, and it's a horizontal line, so perpendicular means that it's vertical. So there's my first perpendicular bisector, and I'll stretch it out, make it nice and big so it's easy to be seen. I'll change the color so it's a little bit, I want to make it a color that's going to stand out really well. How about purple? Does that stand out a little bit better? Looks good to me. So now we're going to do the exact same thing. We'll get a pink color this time. So again, let's find the perpendicular bisector of this vertical line. Well, the one corner is at 0, the other corner is at -6. Yeah. So the middle is going to be at -3, and the line is a vertical line. So if we want a perpendicular one, we want it to be horizontal. And of course, I want to get a horizontal line, not a vertical line. That would be great. Like that, right? Now, I could go through and I could figure out the last one, but I already have 2. If the 2 of them meet here, is the third one also going to meet here? Yeah, right? So we don't need all 3, which is nice. We only need to find 2, and then the third one we get for free. It would be going through this same spot. And so, where is our circumcenter going to have to be? It's going to have to be right here at the point -2, -3, right? So that's one way. That's one way to do a problem like this. Let me show you another way now. Rid of all of this. Go away. Go away. There we go. All right. So remember, we said that the circumcenter happens in certain places for certain types of triangles. And if you look, this line is on the x-axis, this line is on the y-axis. This is obviously a right triangle. Right? This is obviously a right triangle because one side is horizontal, one side is vertical. These two meet at a right angle. It's got to be a right triangle. So that means that the circumcenter is just in the middle of the hypotenuse. So where's the middle? Well, okay, look, here we've got that point here. We've got that point here. Well, what's halfway in between 0 and -4? -2. What's halfway between 0 and -6? -3. So let's find the point -2, -3. Right there in the middle of the hypotenuse, just like we said it was going to be. So you've got 2 different ways that you can do this. You can literally just take your finger on your screen and just follow it along and find the spot where they match. Or if you know it's a right triangle, you can go through and just find the midpoint of the hypotenuse. Either way, you're going to get the same answer. And either way, you're going to be correct. All right? So what I want to do now is I want to give you all a chance to try this on your own. Give this a try. Make sure you're capable. All righty. So once again, there's a couple different ways you can do this, and you're going to get the same answer either way. I'm not going to tell you if, one way is better than the other, because it's not. It's fine to do it either way. The first thing you can notice is, again, we've got a right triangle. I'm giving you right triangles. These are given to you on purpose. There's a right triangle. So if I can put together two of these perpendicular bisectors, then I'm going to do it. So let's find what's halfway between the sides here. This one's an easy one to do. It's a horizontal line. What's halfway in between? Oh, it's here. Oh, look, the axis is already there. I mean, let's just basically highlight the axis so that with a vertical line, highlight the axis with a vertical line because it's a vertical axis. Let's just highlight it so that we can see it. Hey, it's going to be somewhere along here. And if I go through and I do another one, well, let's find halfway in between. It's going to be here. It's not going to let me. Oh, because it wants to go that way. Really? I want you to go this way. There we go. Perpendicular bisector here goes through this spot. So when you follow everything through, there we go. You follow everything through, you're going to get right here. Now you could do that. You could, again, it's okay for you to like sort of just trace along your screen and find that spot. Or, oh, or you could say to yourself, all right, I know this is a right angle. These two lines are perpendicular to each other, right? This has a slope of -1. This has a slope of +1. They have opposite reciprocal slopes. So this is a right triangle. And then you go through and you say, all right, well, hold on a minute. That means it's just got to be on the midpoint of the hypotenuse. And you can just say, all right, well, that's right here. So the circumcenter here is going to be at the point 0, 0. And that's all there is to it. All right? Don't overthink these. So now let's talk about the other one. So we talked about the perpendicular bisectors, and now we're going to talk about the angle bisectors. And basically, in every way, this situation is the opposite of the last situation. Here, instead of finding where the angle bisectors, instead of finding where the perpendicular bisectors meet, we're finding where the angle bisectors meet. And here, instead of it being the distance to the vertices, it's the distance to the side. So it's sort of kind of the opposite way. The perpendicular distance is equal, and we're connecting from the corners to build it, versus the last one where the perpendicular distances are how we form it, and connecting to the corners, they're equal. It's basically just backwards. But the point of this is here. These three are the same. And what's really cool about this one, unlike the last one where the circumcenter could be inside, it could be outside, here it'll always be inside. Because again, we've got these three lines are the same. That means that there's a circle that we draw on the inside of the triangle. So it's always going to be on the inside of the triangle because of this. That's why we call it the incenter, because it's inscribed, as opposed to the circumcenter, because the circle was circumscribed. All right, so let's, again, same idea. Let's do some examples of this now. So now take a look. It says that GE is 2x minus 7. GF is x plus 4. Well, if we're looking at this, this is the G is the incenter, and the distance perpendicular to the sides is the same. So that means that these two are the same. So that means that we can find our value of x out of this. And then, we solve for x. We subtract x from both sides. You can add 7 to both sides. Get x by itself. Finally, we get x equals 11. And so we're going to go through and we're going to say, all right, well, what is it actually asking for? Well, it wants to know what is GD. GD is this one. It's the other one of these. But we know all these are the same. So does it matter about which one we use? If we find one of them, we have them all, right? They all have better be the same. If I plug in 11 to this one, 22 minus 7 had better be 15. If I plug it into this one, 11 plus 4 had better be 15. Well, if this is 15 and this is 15, what must the one that we actually have, what must the answer be? It had better be the same thing. It had better also be 15. Right? So the measure of GD had better be the same as the other two. It had better be 15. All right. So we're going to try, it's going to be the exact same idea, just different numbers and a different picture, but the same idea. So go ahead, give this one a try yourself. Alrighty. So let's go over this one. Once again, QN and QM are all the same because these are the perpendicular distances to the sides from the incenter. So they're the same. We're just going to solve for x just like we do. Let's take the 2x and subtract it over. Subtract 36 over. Then divide both sides by 3. And so we're going to go in and we're going to double check our work. Plug it in. 25 plus 36 had better be 61. 10 plus 51 had better be also 61. Hey, we know that what we've done is right. QM, 61. QN, 61. We want to know what QO is. Well, it had also better be 61. Again, look at the question, right? Now there was an alternative question in here as well, saying, okay, well, is it possible that QL could ever be 50? And we can answer that question with a definite no, right? And the reason we know is because of the definition of distance from a point to a line. If the distance from point to a line is the perpendicular distance like this from here, from Q to N, that means that from Q to N is the shortest distance from Q to this side, right? If this goes further, if I'm going away from spot N, it's taking me longer to get to this segment KL. And so therefore, any other amount of walking time has to be a bigger amount of walking time. So how can I be less than 61? I can't. If the quickest route is 61 feet, going any other route is going to take significantly more than 61 feet. And that's the idea.